Hello friends, so today we're gonna discuss these problems from the NOMURA Programming Competition 2020. In this video we will discuss the top 3 questions and then the subsequent videos will consist of all the later questions. The first question statement states that in this problem we use a 24-hour clock and Takashi get up exactly at M1 like H1 M1. So these are the this is the time given at which Takahashi will wake up and this is the time at which Takahashi will go to bed, and he had decided to study for k consecutive minutes while he is up. What is the length of the period in which he can start studying? So as you can see, I'll take your small example to tell you the question statement. If you wake up at 5 o'clock in the morning, and then you go at sleep at 6 o'clock in the morning, then the time you wake up is 1 hour. And let's say you want to study for 30 minutes. So if you start studying at 5 o'clock, when the time you wake up, you can easily study for 30 minutes, and you can study till 5:30, and then you can easily go to bed at 6. But let's assume you want to study from like 5:35, then you cannot study for half an hour because you want to go at sleep at 6 o'clock, and thus they are asking us what is the time in which you can start studying such that you can complete your study time within the before the time when you sleep. So that's the question. So how you can easily find out? You can find out the total slab of the time in which you will wake up, and you will subtract it from the time you will study. Also, as you can see, if you wake up for only 1 hour and you want to study for like 2 hours, how you can do? So then there is no slab, zero, for which you can study. So there are these two cases in which if you wake up like at this and this, and you want to study for this time, there is exactly no slab. So then you can easily do this by this directly tell you the code, in which you take the time input of M1 like H1 M1 H2 M2 and K, and then the total time like taken in which you will be up is H2 minus H1 into 60 because these are for hours, and then you will subtract the minute time, or like add, sorry, and then the final answer will be maximum of the total minus k or 0, because if it's turned out to be negative, then the answer will be not be negative, it will be 0. So that's the logic for the first question. Let's move to the second question. There's a trick in this question. I haven't seen it when I was solving this question, but after I see some solutions or the tutorial, then I got the trick, but I haven't like understand the trick. I'll tell you both of the solutions. So the question statement states that you are given a string consisting of only P and D, and what you will see here is like as you can see, if this is the string given, let doctoral and postdoctoral coefficient or quotient of S be the total number of occurrence of D and PD as a contiguous substring. So as you can see in this string, you have to count out how many total D appears and PD appears. So that's the total score or the postdoctoral and doctoral quotient of that string. So as you can see, there are two D's and only one PD. So the answer is for 3. But in the string you are given P, D and question marks. So you have to fill question marks with either P and D such that you have to maximize the doctoral and postdoctoral quotient. So as you can see, I'll tell you how I initially solved it, in which what I did was I take out the following cases in which it can occur. The cases can be, there can be two question mark at the same position, P and a question mark, a dash, like question mark and a P, D and a question mark and D. So these are the possible 5 cases in which there can be a case, because we have to locally maximize such that the answer will be greedily or like more globally maximized. This is just a greedy approach in which if there are two question marks, I can just put a P and D here. If there is a P here and there's a question mark, I will prefer to put a D here. If there is a P here, I will put a D here because I want to maximize the score. If there is a D, I will put a D. If there is a D, I will put a P. And these are the 5 cases I can like brute forcefully like write these or like hardcode all these cases, and then the answer is correct. But the case which I missed out here is Actually, if you just see PD as an individual is giving you a score of 2 because PD is counted as 1 and D is counted as 1. But if you just take DD, this is also giving you a score of 2 only. Now, in every case, as you can see, putting D is just a waste. So you don't have to put P, sorry, putting P is just a waste. We have to just only put D in every question mark and then the answer is also correct for that. So that's the two examples. So the thing is, in the first thing I told you, I have hard coded all the cases in which if there's a question mark and then there's a previous term which is P and the you can see this. I have hard coded every case there, and then I have just written down if there are two question marks, if SI is question mark and SI plus one exists, and it's a question mark then P and D. If it's a question mark and like if the next question is D, then it should be P. If this is just a question mark, it's just a D, and then I printed out the string S, and this is also giving you the correct answer. Or else I have just written on in the comment. You can iterate over the whole position in the string and see whether it's a question mark. You can just put D here, and that will also work fine. Now moving on to the last question. It's a very interesting problem according to me, in which you are given actually a sequence of integers from till n plus 1, and you have to tell whether there is a binary tree exists of depth n such that at each depth there are exactly 80 leaves. So this is actually the number of leaves at each depth. So you want to find out whether there is a binary tree which exists such that the number of leaves at each depth is equal to this number. If it exists, you have to return out the number of vertices or the number of nodes in that tree. Else you have to return that tree doesn't exist and you want to print minus. I hope you understand the question. The example will make it more clear. As you can see for this, number of leaves at the 0th depth is 0 because this is a node, this is not a leaf. There is one leaf at the first depth, and the second depth there is also one leaf, and there are two leaves at this depth. But we'll do it for this example, and the logic and the example will make it more clear how we will solve this question. So we will first take the starting node, and we will have this given array, which is the input, which tell us how many leaves are there at each depth. We can also maintain an array, additional array, which will tell us how many non-leaves are there at each depth. Because as you can see, at this depth there is one non-leaf, this is one non-leaf, and this is one leaf. And if you want to count out how many total number of nodes are there, we can count out at each depth how many nodes are there which are leaves and how many nodes are there which are non-leaves. So this is the first point. So we have to first count out how many leaves are there and how many non-leaves are there. So, but can every node has two children? No, because it's a binary tree. Though every child has a maximum of two children, but every children will not definitely have two children. We have to find out. This is also one point. We have to find out the maximum possible number of vertices. Okay. So what we will do is we will start building this tree according to this number of leaves and see how we can find out. We have also found out the prefix sum for all this number, and I will tell you why I found it out. But let's start building the tree first. So at the first depth, 0 depth, there is no leaves. So this means that this is not a leaf, and it will be consisting of two children. Definitely. And thus we can observe all the nodes which are not leaf will multiply by 2 at each depth. Every node which is not a leaf will multiply at the next step by 2. So now there are 2 nodes at this step. And as you can again see, there are no leaves at this. So we have either option to multiply all the two nodes, or we can either do this also. But we cannot just do this, because if we just do this, this leaf or else like this leaf will form a leaf, this node, and we will have to at least take out one like one path or like one vertex from both of these nodes to not make them a leaf. Then after making out taking out the choice, we will make use of this prefix sum. So now, because in the end we want our answer, or we want that the total number of leaves in the total tree should be only equal to 3, and at any position we should not exceed that. So the thing is, at this position we will always find out, because like see, at this position we want to find out how many leaves are there and whether what is the minimum of them. Yeah. So because this prefix sum tells us how many leaves are there. Okay. So now if at every position, at every depth, we know that there are these number of nodes which will be formed from the non-leaf. So two nodes will be forming from the non-leaf, and this depth, at this depth we'll know that there are no leaves. So now they will all either branch down, or one of them will branch down, or so on. So we will check it from this prefix. So we will check like how many more leaves are still on the way to come in this tree. So because we are up to this point, we will do a prefix sum from this point to this point, which is actually 3. So we will do a subtraction from this point to this point. So 0 minus 3 actually gives us 3, which will tell us that there are still 3 more leaves to come. And now we will know that because there are 3 more leaves to come, we will do the minimum of the number of non-leaves and this prefix sum, which will tell us the minimum at this point is 2, the number of non-leaves at this point is 2, and this is 3. So we will tell, yeah, how many number of non-leaves will stay there, or the number of non-leaves will be there at each depth. So number of non-leaves at this depth will remain 2. Now this will multiply and become 4. Now as you can see, now because it becomes 4, how many leaves are there at this position? There is 1 leaf. So this will become a leaf, and we will not touch that. Now we have 3 non-leaf nodes, and we have to see whether we want to still take all the leaves, we want to branch every leaf or not. But now as we can see, if we do a minimum of, it will become a 3 minus 1, it will become 2, because we want to find a minimum, we want to find a prefix sum of this, which is just this, or actually we will subtract 3 minus 1, which is 2, and we will find the minimum of 2 and 3, which is 2, which will actually help us to tell us that at this point we are stating that if this is only the tree, there are 3 leaves, but we want in the end only 2 leaves. So we will only branch them down such that there will be only 2 vertices, which will help us in the next depth. If they said that at the next depth we only want two nodes, because now if we branch them into four parts, or like into 3 parts, then everyone will branch out. But what we can do either is, we can make this a leaf, and now the minimum of them is 3 and 2, it's just 2. So we make it like this. This is also perfect. Now there are two non-leaves and they will again multiply. They can again become like this or singular also. So we want to check the minimum at this point is the prefix of this, which is again 2. You can easily find out 3 minus 1, which is 2, and then which means this will happen. And now in the end, the number of leaves should become equal to this. The number of leaves become equal to the number of nodes which we are calculating at every step. And when we have seen that the tree has built and we haven't gone out of constraints, so then we can see that this tree is perfect. So I'll tell you how the code works now. So I have taken the output for n, and because it is 3 and the number of inputs is 3 plus 1, n plus 1, so n plus 1 is the leaves, and is the input of all the leaves because it's from 0 till n. Then if the first leaf is greater than or equal to 2, we can check it. And the answer is just minus 1 because the first leaf can be having at most 0 or 1 children. It cannot go above 2. Then we will find out the prefix, which is just the prefix of these leaves. Then we will make a vector for the non-leaves, and then the non-leaf first value is just 1 minus the number of leaf at the first position. Then we'll do a for loop, and then at every position we'll double the number of non-leaves at the above depth. So at the ith depth we will find out how many non-leaves are there at the ith minus 1 depth, double it, and then subtract it from the number of leaves which are given at this ith depth, because the number of non-leaves at any depth is equal to the number of non-leaves at the above depth minus the number of leaves which we are given in the array at this depth. So at the ith depth, these are the number of non-leaves, but whether all these non-leaves multiply in the next I plus 1 depth, so we have to modify this number of non-leaves at this ith depth, which is just the minimum of number of non-leaves and the sum of n plus 1 minus I plus 1. So we are just finding out the prefix, and if it goes below 0, we are just printing out minus 1 because it goes out of constraints, out of bound, and else actually this is showing the number of non-leaves at every depth. Then we'll do a for loop and store the answer from 0 till n, like find out the total answer for all the number of leaves and the non-leaves at every depth, and then print out the answer. I hope you understand the logic as well as the code. If you still have any doubt, please mention it in the comment box. I'll try to rectify it as soon as possible. If you like these explanations, please hit the like button and subscribe to my channel. I'll see you in the next one.